So our next topic is on database normalization, and it is lecture number 6B, and we will have a couple of normalized questions on the final exam, so it's not a bad idea to become familiar with the different normal forms. It wouldn't be a database class unless I talked about normalization, so here we go. Normalization of a database is how we're judging the quality of the table's construction and what it is that makes it fall into normal form 1, 2, or 3. Why don't we want to go higher than 3? And what is this Bcnf form? And maybe we could be in third in Bcnf. And all the things associated with what are good characteristics of a database design. So in this lecture we're going to look at normalization, what it is, what role it plays in database processing, or database design process I should say. We're going to take a look at the normal forms and what it means to be in each one of them, and how normal forms can be transformed from one lower normal form to a higher normal form. I believe we also have an assignment on the normal forms, and it is assignment number 6, I believe. 7? It's CSLO 6. The 6, assignment number 6, I believe, is on normalization. Let me just take a quick peek here, actually, so I'm not misquoting you. And I thought I had these assignments downloaded, and I don't see them here, actually. So I'll take a look at that well, here, let me just go out real quick here and take a look. I was searching on Apple logos during the break. Let's see, I believe it is assignment number 6, but let's just take a look. We have number 5. Let's take a look at assignment number 5 then. Let me take a look at number 4 while I'm here as well. Assignment number 5 is on normalization. So it's hard to see it from where you're sitting, but so let me make this a little bit bigger. Zoom in. I will wait and go over this assignment after I'm done with the normalization lecture, but number 5 is going to be applied to this lecture. So if you're looking for help with number 5, it is on the database lecture 6B. 6B is the PowerPoint that goes along with assignment number 5. And I believe assignment number 4 is the comparison with the object-oriented databases, with the hierarchical databases, with relational model. But I'll make sure before we end today, probably after lunch, I'll go over the different types of database systems in terms of what you need to know for that assignment. Actually, I think I've actually already covered that in the beginning, first weekend of the class. So instead, I'll just go over the assignment probably. So what normalization is, how it works, and that normalization and entity relationship modeling are used concurrently to produce good database designs. And what are some of the situations that require denormalization? And why would you want to denormalize something, take something out of third normal form and put it into second normal form? Well, I can tell you in a nutshell that the higher the normal form, the harder it is to query the database. So you get to a certain point where you can't get the data out of the database. It's too high level. And then if you lower the forms a little bit, it makes it easier to query. What does that mean? Well, reduce the number of joins that you have to do. Add some controlled redundancy in there. Reduces the normal form a little bit, not so much. Doesn't put it back into first normal form. First normal form is not so good. Second and third normal form are okay. You go into fourth, fifth, sixth, and the normal forms do go higher. Not so workable. So third normal form is about the average that most databases are put into. So normalization. So talks about the structure of the tables. So normalization is the process of evaluating and correcting the table structures to minimize the data redundancies. We want consistency, and we want a lack of redundancy in the data, and we want to introduce what's called controlled redundancy. So we put redundancy in to remove undesirable redundancy. So the foreign keys, the primary keys, all of the keys that we're putting in is introducing redundancy. We have a student ID in one table. We have a student ID in all the other tables. Isn't that a little bit redundant? But it's controlled redundancy because it's a key, and the key is acting as a primary in one table and a foreign in all these other tables. So it gives us the ability to kind of link things up, and separate things out, and reduce the amount of other redundancy that might exist in the tables. So it helps eliminate data anomalies as well, and it helps to hopefully make the data searchable and findable. So it works through a series of stages called normalization or normal forms. And we have normal form 1, first normal form, second normal form, third normal form, that this lecture is going to talk about. Excuse me, my voice keeps going. Database tables and normalization in terms of what's a second normal form. Well, the higher we go on the normal forms, the better form we're in, to a certain point. It's almost like being too strict at one point. So second is better than first, third is better than second. Do we want to go up higher than third, or third and Bcnf, and I'll talk about Bcnf in a few minutes as well? Probably not, because then it makes it harder to actually search on the data. And we have to do more joins. It's less efficient. So the higher we go up in the normal forms, the more tables we're normally creating, the less efficient the searches are actually going to be, but the more accurate the results are going to be in the end. So for most businesses in their design, third normal form is the highest you need to go in the normalization process. The highest level of normalization is not always the more desirable. So in terms of our need for normalization, we have a company that manages building projects. So I'm going to go through a sample scenario that's going to take a spreadsheet that was created in Microsoft Excel. It's going to put it into a database table, which is really first normal form, and then go through the normalization process to turn that into third normal form. So in the sample scenario, this company charges its clients for billing hours that are spent on each one of the contracts. And the hourly billing rate is dependent on the employee's position. His level is going to cost more if he's more senior, less if he's junior. And periodically a report is generated that contains information that's displayed in Table 5.1. Well, here's Table 5.1. So believe it or not, that's sort of like a spreadsheet actually. And it's a report. And what ends up happening is a lot of business managers, because imagine they're not database people, but business managers do this all the time. They go, here, I want a database, here's the report. And take this report and put it into a database. And usually the same person will go, wait a minute now, that's not really how it works. But the business manager will insist upon it, and they'll do it themselves sometimes as well. And so you get this report that gets turned into a database. That's actually a first normal form database table. You can stick that in a table, no problem. It looks like a table, right? It's got columns, it's got rows. So that's why business people think it should go into a table when, that's really not the overall design, but that happens. So if you took this thing here and you put it into a table, it'd look like this. And this is a picture of Microsoft Access, actually. And here's a table in the report format. And I've seen a lot of this, actually, and it happens all the time. And I wonder, why do people do this? It's because they don't understand the concept of the database. Because Access comes with Excel and Office and everything. And people that use Microsoft Access do this all the time. And they go, oh, it's a table. We put it into a database. And I'm thinking, why don't you just use Excel for this? Because this is really an Excel spreadsheet that you put in a Microsoft Access table. But what you're looking at is kind of a first normal form, but not really. It's almost first normal form. You have some repeated groups and you have some missing information for some groups. So the structure of this thing up here, just imagine a spreadsheet of some sort, doesn't handle data very well. The table structure appears to work. The report is generated with ease. You just print out the table and you get the report. But unfortunately, the report may yield different results depending upon what data anomalies have occurred. If you do a query on that, you're going to get some interesting results that come out of that. Maybe not so valuable. So let's convert it into first normal form. So if someone tells you that your database isn't even in first normal form, they're really being insulting because they're telling you it looks like this, which is like an Excel spreadsheet. So we can put it into first normal form, and if we do that, we get rid of the repeating groups. So repeating groups. First normal form databases normally have repeating groups in them. So it derives its name from the fact that the groups of the multiple related entries can exist for any single key attribute occurrence. And we're going to see the repeating groups in a few minutes. The relation table must not contain any repeating groups. So normalization and normalizing the table structure will reduce these data redundancies, get rid of the repeats, and we have a 3-step process that we're going to go through. So first step for number 1, to get it into normal form, we're going to eliminate the repeating groups. So present the present data in the tabular format that we saw it in the spreadsheet, where each cell has a single value and there are no repeating groups. So eliminate the repeating groups by eliminating the nulls, or the empty spaces, making sure that each repeating group attribute contains an appropriate data value. So here's our data organization in first normal form. I introduced redundancy to get rid of this here. That's not in first normal form yet. It's not in first normal form because we have empties here. If I sorted this differently, I'm going to have some information in that's missing because of and this is called a repeating group. So the repeating group says project number 15 in the name, and we have all these employees that are working on project number 15. Well, that's a group, and then the group repeats with different project numbers. So now we have this. That's a first normal form database. It's still kind of insulting if someone were to tell me, well, that's true. We have evergreen, 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 evergreen. So now if we sort it or we do queries on it, it's first normal form. So it's not the most desirable format, but it's still more searchable, or accuracy. We get a little higher level accuracy with the results because we don't have any blanks in here. So we can now sort it. And we can sort it and we can search through it. We can actually run a query on this too if we wanted to. Well, we have a project number, project name. Well, we have 1515 evergreen, evergreen. That's kind of redundant. So in step number 2, so step number 1 is get rid of all repeating groups, eliminate the repeating groups. So when we do that, we're in first normal form. Step number 2 is identify primary keys. Primary key must uniquely identify attribute values. So new key must be composed. And then in step number 3, we identify all of the dependencies that are on those primary keys. So dependencies can be depicted with the help of a diagram, dependency diagram. Remember, first weekend I showed you dependency diagrams and entity relationship diagrams. That's a form of a dependency diagram. So it depicts all of the dependencies found within a given table structure. Helpful in getting rid of getting the bird's eye view of all the relationships among the different table attributes, and makes use makes it much easier. Likely more important dependencies will be overlooked. So instead of taking this approach and taking a spreadsheet and putting it into a table, if we start out with a business concept, write an entity relationship diagram, take the diagram, translate it into a list of tables, take the tables and put it into the database, we're in second normal form automatically, which is not bad. Second normal, actually we could even be in third normal form. The diagram is, if you identify all of the primaries and the foreign keys and you consider all of the relationships correctly, you're most likely going to be in third normal form. So but you're at least second, probably in third normal form by the time you translate it. So here's a dependency diagram for first normal form. And we have, without doing the entity relationship diagram, just by throwing darts out there and putting stuff in a table without considering any of the dependencies, we end up with partial dependencies and transitive dependencies as a side effect. So here we have a partial dependency where we have project name and project number as a classic example. In fact, this happens all the time where you say project number 1, it's called Java programming. Actually, we see this with classes in the student class list. So I can tell you the EMS, I don't know if it's been fixed yet, but it had a partial dependency, which meant you could put a code in there, but the name didn't have to match for each one of the codes. So if it was SEN 9, what is this class called? 985 or something. The name of it kept changing. So it was, oh, it's Oracle Database and Administration. Then for one term it was Oracle Database, and then it was Oracle, and then it was Database Concepts, and then it was, well, which means you don't want partial dependencies. So every time you use the class code SEN 985, you want it to come out with the name that's identical. That's a full dependency, that's not a partial. Partial means we have a name that's associated with a number, but there's no requirement in the database that it be the same. Well, if the number was a key, then the name would actually be required to be the same, and we'd pull the name from the number. So one would determine the other instead of there being a free flow partial kind of thing going on. So then we have the employee project number with employee number. Employee number has a partial dependency with the employee name, employee job code, and charged hour. And then we have a transitive dependency with job class and job hour. Because not every single, it depends on the job class per another one. So a transitive dependency is a circular dependency that relies upon another key. So it depends on who the employee is and what their job class is in terms of what their charged hour is. Because the charged hours per job class change depending upon which employee we're talking about. So if we put it all in a flat database like this, that'd be like, well, student A, B, and C, depending upon which student and what level, your tuition is different. So international student A and international student B could be paying 2 different tuition rates. That's a transitive dependency. Because it doesn't depend on whether you're an international student, it depends on who you are, which is a totally transitive. It's outside of the relationship between the rate and the pay. So it's depending upon another key, and it's depending upon who the other person is. So we don't want that either. But our first normal form has all this stuff. So we get it out of first normal form, we put it into second where we get rid of the partial dependencies, and then we get it into third when we get rid of transitive dependencies. And then we have a third normal form database. Well, how do we do that? Well, we just break this out and put it into other tables, and then we introduce controlled redundancy. Controlled redundancy is the keys. So we break it all out so we can put it all back together, and we enforce database constraints through the key relationships. So first normal form is a tabular format in which all the key attributes are defined. There are no repeating groups in the table, hopefully, and all attributes are dependent on a primary key. And then all relational tables satisfy the first normal form requirement. Some tables might contain partial dependencies, dependencies based on only part of a primary key, but not all of it. So that's how the name here, the partial dependency I gave you here is, yeah, it's the database class. It's relying upon it, but not all of it. It's not a strict reliance upon the number of the course to get the description of the course. When it shouldn't be a partial, it should be a full dependency. And then sometimes used for performance reasons, but should be used with caution. You can put in a, if you have this in here, if you have the project number and the project name, or the class number, class name, in a table, you don't have to link this together. Because if I gave you a project number or a class number, you'd have to go look up the name in another table in order to use it. So for efficiency reasons, we can actually put it in to one table, create this partial dependency as long as we have business rules that make it required. So we can put a check on the field to make it require. It has to go look up in we could actually put a lookup in here. So you add a new course, and how do you add in? How often are you going to add a new course? Not too often. So instead, you put the inefficiency on that add process. So to add a course, then you have to go look it up in another course to make sure it matches, and you have to do a manual check on it as a business rule, which is essentially what we've done. But you've noticed probably that, and maybe not with this class, but with other classes in the past, we have class names that don't match class codes. And then annually or semi-annually, the administration goes through and cleans it up. But I'm sure somebody out here has got a transcript that has a class number that's different than, the description is different than something else that another student has, and it's the same class code, which is kind of interesting. It depends on when you took it as to what they called it. So anyway, it's because there's a partial dependency, it's not a full. So it's still subject to data redundancies as well. So it's every single one of these fields. And when we're talking about data redundancies, that every single record that uses this project number has a project name in it. Hopefully the project name matches, but it doesn't have to. But it's in every single row. Why was it in every single row? That's redundant. The more information we're putting in each one of the tables, the bigger the tables are, the more memory they take up. So let's go into second normal form. So the relational database design can be improved by converting the database into second normal form. There's a two-step process. Step number one We identify all the key components. So we pull the keys out. Write each key component on a separate line. It's going to turn into a separate table. And then write the original composite key on the last line. Each component will become a key in the new table. And then we identify the dependent attributes. Aren't we just doing an entity relationship diagram at this point, but backwards? So we took the data that we had in one big old table and we broke it out into smaller tables. Is what we're doing. And so we're really doing an entity relationship in the exact opposite order. So determine which attributes are dependent on which other attributes. And we want to get rid of the partial dependencies. So at this point, most of the anomalies have been eliminated. So if we take that first normal form database and we put it into second normal form, it looks like this. It's still not third normal form. So that's why I say some of your entity relationship diagrams will do this if you're not looking at transitive relationships. So this is a second normal form database where we pulled out this one. This is a no-brainer. This is like the class and the class description. That should be a separate table actually. Project number and project name, separate table. And then we link up project number here with project number with project number, which means now we've introduced more redundancy, but this is what they call controlled redundancy. So when the redundancy is a key, it's controlled. That's okay. If the redundancy is not a key, it's bad redundancy. It puts you down into first or second normal form depending upon the other issues that might exist. And this is the other issue here that's leaving it. This is leaving it in second normal and not third normal form. So we have project number, project number, project number, and then we have project number, employee number, and we have employee name, and then we have employee name and employee number. So we have two foreign keys with a primary key and a primary key, which is good. But then we have this transitive relationship here. We still have this problem with the employee that might make difference. So employee A with job class 1 makes $10 an hour. Employee B with job class 1 might be making $12 an hour. So it depends on which employee, same job class. So with the job class here, if we wanted to make this more reliable, we could put it in a third normal form and get rid of this transitive dependency. So this one's called project, this one's called employee, and this one's called assignment or works on. So now we have 3 tables instead of just 1 table. And now we're in second normal form. So second normal form, just to remind you, is that a table that is also in first normal form. If it's in second, it's also in first automatically. But it includes no partial dependencies. We take out the partial dependencies, a second normal form table. Each table has a primary key, and then the tables that are linking it together have the foreign keys. So this is really a second normal form concept. All the partial dependencies are removed, and now we have the key system put in. In the first normal form, we don't have any keys in this table. We have dependencies going on, we have partial dependencies, but these really aren't keys. They're not being used as keys. We're not linking it together. We only have one table with this. So they're in different colors to show you where they're dependent, but they're not different. They're all in one table. So let's go into third normal form. To go into third normal form, we look at the data anomalies that are created, and we eliminate by completing 3 steps. Identify each new determinant. So what we're really looking at is the transitive relationships. So for every transitive dependency, write its determinant as a primary key in a new table. So what's a determinant? It's an attribute whose value determines another value within the row. So the determinant up here is that according to your job class, you should be making a certain amount per hour. So if the job class is going to determine how much you're making per hour, that's a determinant, which means that's a key. So in here we have, a key combo. We have 2 primaries essentially inside of one table. You don't want 2 primaries in one table. That's a dead giveaway right there. So if you're trying to take this and you're trying to figure out if you have a second normal form or a third normal form, just look at the table structure. If you have any table, so these 2 tables are good. That table's good, that table's good. But this table's not good. So my entire database is not in third, it's in second normal form. If I have two primaries in one table, I got a problem. I'm in second normal form. Pull it out, put it in third normal form. How do you know that's a primary? See, the person who put this together didn't make this green. Never made it green, never thought about it as being a primary. But this one is dependent on this one, or we think it should be, like the job class. If you're class A, B, or C, all employees who are A, B, or C who fall into the job class should be making the same amount per hour, shouldn't they? It's kind of like the way the world works. Well, if we want to make it the way the world works, then we get rid of the transitive dependency. It doesn't really matter who it is. You know, just because Mary's job class A and Bob is job class A, why is Mary making more than Bob when they should be making the same thing if they're both job class A? Otherwise, why have a job class if that's the case? So it's kind of like if we're all seniors, then some of us get to graduate and some of us don't get to graduate. Well, that's because of our units. So if some of us still have to take classes, why are we seniors? So, but that rule never changes. Depends on how many years of school you've gone through, whether you're a sophomore, junior, or senior. So whatever. Sophomore, junior, freshman, sophomore, junior, senior. I'm like leaving out freshman. Or if you're, actually that's the funny thing, because if you're a graduate student, you're just a graduate student. You're not in any of the categories. So you're post-grad. Means after you're a graduate student, now you're another student again. You're a postgraduate student. All right, so we have the determinant. That's what the determinant's about. So you're identifying the dependent attributes. So identify the attributes that are dependent on each determinant identified in step 1, and then identify the dependencies that are associated with it. And then name the table to reflect its contents and its function. So you're going to create another table. So you're going to remove the dependency attribute from the transitive dependency, get rid of the transitive dependency, create a new table to represent the information, and then eliminate it. So eliminate all the dependent attributes in the transitive relationship from each table. You have to go through each table to do this, such that there's no transitive relationship. Draw a new dependency diagram if you're doing a diagram. Check the new tables, and then modify the tables from step 3 to make sure that each one has a determinant and does not contain inappropriate dependencies. So here we go. Here's our third normal form table that we get out of this. We took this and we branched it off on its own. Now we have a third normal form database. It's third normal form because all tables meet third normal form requirements. There's no partial and there's no transitive dependencies. So we can have partial and transitive in first normal form. In second, we don't have any partials, but we might have some transitive. In third, we have neither transitive nor partials. So what we have now is an employee over here, and then we have a job class. The job class is a job class over here, and the job class over here gives us an hour. So now Bob and Mary, that are both job class A, are making the same amount of money per hour. So Mary's probably not going to like that, but Bob's going to be feeling like it's more fair. And if we did this with the class numbers, then anyone who took SCN 985 would be taking Oracle Database Administration and something else. I don't know what this class is even called personally. But you'd be taking something with the same class name. So all your class names line up, all your job classes line up with the right pay. But we're not done. We can actually improve this even further. So this is a third normal form database. Actually, I think this one is also Bcnf, but we'll see. So third normal form, if it's in second normal form, if it's in second, it's also in first. So if I asked you on a multiple choice test, I said, if a database is in third normal form, is it also in second? Yes. Is it also in first? Yes. You know, about 50% of the class missed this the last time I asked that question. And I'm like, wow, how could you miss that question? It's like, well, because they're like, no, it's in third normal form. How can it be in second? It's already in third. It's in all. It's in first, second, and third, by the way. It's in everything. Is it in Bcnf? No, may not be. May not be in Bcnf. I'm going to talk about Bcnf next. I haven't talked about that yet. So what's characteristic of third normal form? No transitive relationships. What's characteristics of second normal form? Some transitive relationships, but no partial dependencies. So those are the distinctions there. So we can improve the design even further. So the table structures are cleaned up to eliminate the troublesome initial, partial, and transitive dependencies. So transitive dependencies and partial dependencies are the two things we're fixing. Normalization can't in itself be relied upon for good designs. We have to actually think a little bit more about it. It's valuable because it uses or it helps eliminate data redundancies and introduces controlled redundancies. So we can improve the design even further. Following changes were made when we made this design to put it into third normal form. We created primary keys. We used naming conventions of tables to hopefully, instead of saying table A, table B, and table C, which, believe it or not, people used to do. And you're like, why don't you just call it students, faculties, and classes or something? Attribute automaticity, which means make them all the same. And adding attributes to tables to make the information more specific, adding relationships, refining the primary keys, maintaining historical accuracy, and then using derived attributes instead of like putting in an age instead of a date of birth. So the complete database looks like this, where we have a project with a job. The job has a job code, a job description, job hours. And then we have who works on it. So if we were to rebuild this, I'm not going to have you do it for this class. I had a third assignment or third project that I decided was too complicated. It was worse than the assignment. Well, the assignment's pretty easy. I'll go over the assignment last, but I had another activity I was going to give you, but then I realized after looking at all of the databases from yesterday, a good 80% of you haven't started the second one yet. So this afternoon we'll be doing the second exercise, which is the SQL queries. And the SQL queries can be kind of challenging. The third one is a more advanced normalization activity, where you take a bad database design and you make it better. And then you have to go through this process. But you're going to do it in the assignment, so I figured you probably don't have to do it in class. But make sure when you do the assignment that you kind of study a little bit on the concept, because it'll help you learn what you're doing in terms of translating those tables. And there's a couple of different ways of doing it depending upon what normal form you're actually putting it into. So here's our complete database with all of our tables. So the limitations on the system assigned keys. So in Microsoft Access, and actually in some of the exercises you were doing the other day, you had an ID that was a system assigned auto number. Problems with that. The auto number doesn't mean anything. Not like a social security number means something, or actually not like a student ID really means something. So student ID doesn't really mean anything. It's an auto-generated number. So auto-generated numbers are not bad, they're used all the time. But there's limitations. So system assigned primary keys are not may not prevent confusing entries. Like if you don't remember your student ID, how can you find yourself in the table? So what ends up happening is people search on other data. They don't find the other data because they don't know what the other data is, and that's not kept as a key, so it maybe not necessarily in the data or in the table. And then you get added again with another system assigned ID. I know we have this at ITU because we have students with multiple student IDs. Actually, we have students who have multiple degrees with multiple student IDs. So, which is kind of interesting, actually. And I think they're making an attempt now to remove the multiple IDs, or to at least link them together. So one student who has two student ID, why should a student have more than one student ID? Problem with that is what I'm talking about here is the limitation of system assigned keys. What if the student forgot what their ID was? Actually, the funny thing is the students didn't forget what their IDs was, they were just assigned a new one. Because they were put into the system with a new major. So now you're a sophomore engineer, now you're an engineering management major, now you're an MBA major. If you have multiple degrees or you're going from second major, most likely you're going to get another student ID. But you're the same student. So I still haven't figured that one out yet in terms of, and IT continues to do things that way, which is amazing. But I think we're going down to one ID. I believe I heard Durst talk about it. And then we won't have this problem. We can still be in third normal form, but we have system assigned IDs. If we used your passport number, that might be a problem. If we used your social security number, that might be a problem, especially if you don't have one. So the problem is it's an innate because we have to system assign it. So, and what ended up happening is if we looked up your old ID, we're going to find your old major. And you look up your new ID, we're going to find your new major. That's the only way they can keep you separated in terms of your majors. So it was actually put in on purpose to add redundancy, but not really to add redundancy, but to add accuracy in terms of finding you in the system. So the data entries in 5.2 are inappropriate because there are duplicate existing records. In here, if we look at it, we took the data. If we actually enforced, going back to that spreadsheet, by the way, if we took the data and we actually put it into our complete database with all of our keys, we have to clean the data up because we have duplicate records. Because we had repeating rows that we filled in. So we took the repeating rows, we corrected it, repeating groups, got rid of the groups. Now we have repeating rows, and then we take that. So although the data structure of the database is in third normal form, our data is not. So because of that, repeating groups. We have duplicate entries for the job table, as an example, which could happen actually if we work from the data perspective forward, because in the past we had, we had job code. This is like what we'd have in our database right now if we took it and made class code a primary key and then the description part of the class code table. Then we're going to see, in this particular case, job code 511 and 512. Well, they're both programmers, and one of them's making this amount, one of them's the same amount. But we have two different job codes. So we have two codes for the same, which could be a problem. So when we have a situation where we have repeating entries, it's keyed, but we have repeating entries. We haven't identified them as being unique, or it has only been single valued. So we can only have 511. Well, we do. Actually, we have 511 and we have 512. They're both programmers, and they're both making the same. It's really the same thing, but it's under two different codes. And we haven't violated the key constraint because we have two separate codes, but we have the same thing in there. Well, this is like student ID 511 and student ID 512, and student name, address, telephone number, major, all your other stuff. This is your student ID, by the way. So we're not in Bcnf. IT is not in Bcnf if we have those repeating groups. So Bcnf says that every determinant in the table is a candidate key and has same characteristics as a primary key, but for some reason not chosen to be the primary key. So programmer. So if a table contains only one candidate key, then the 3BNF and the Bcnf are equivalent. Bcnf can be violated only if the table contains more than one candidate key. So if we have more than one candidate, we have student ID, plus we have your social security number, plus we have something else along with that. We could put you in twice because we have more than one candidate key and we can search on you twice. Because we're going to use your name. Actually, I think they use your name, which is why some people have FNU, first name unknown. And then you come out and your transcript says FNU on it. You're like, why is that? Well, because the field couldn't be null. Or is it your last name or your first name? And your name is being used to identify. If you have two student IDs, how are they going to find you in the system? They're going to use your student ID. Well, that's a candidate key. That's a key. That's a primary key for the table. And they have to add you in order to put you in again as a second major. And then they're going to use your name. And your name's going to come out as a secondary candidate key. So this is where the candidate keys come into place. If you have another candidate key in there that can be used to search the table, you're not in Bcnf format. If you only search the table one way, you're in third normal form and Bcnf. So let's take a look at an example here. Most designers consider and this is called voice cod format, or Bcnf, a special case of third normal form. So table is in third normal form if it's in second normal form and there are no transitive dependencies. A table is in third normal form and not in Bcnf if a transitive dependency exists when one of the non-prime attribute is dependent on another non-prime attribute. And a non-key attribute is dependent on a key attribute. Your name in the table with your student ID, multiple student IDs in the table, that's a dependency. Because they got to find you under two. They got to find you under your name and your student ID. Otherwise, if they just looked at your student ID, you'd come out with only one degree. So if you're going to do a transcript and you have multiple degrees, actually that's interesting. Do you do it when you get a transcript from this school? Do you have multiple degrees on it, or do you only have one degree? Well, you don't know because you guys are still students. If I went to another school like San Jose State as an example, and you got a bachelor's degree and a master's degree, when you pull the transcript, you're going to see the bachelor's degree and the master's degree together under one student ID. So I'm kind of curious, maybe I need to ask the administration what happens. Do you get 2 transcripts? Because you're the same student, but you got 2 different IDs. So how does that work? So that's an interesting kind of question, but I know that their new system doesn't like the idea that there's 2 IDs. So I know you're probably going to be reduced down to 1 in the future, if you're not already. But there are some students who have been here for a while who still have 2. They have an old one and a new one. So I guess you get just to have like overs. You know, you can just start over again. Get a new everything. Is it linked? I'm pretty sure it should be linked. It has to be linked. So that'd be interesting. I'm gonna have to ask that question actually. How do you get when you get your grades? Well, you guys don't get grade reports, do you? Do you guys get grade reports? Like you know, is it all online? You can check your grades online. I guess you can order a transcript online.
You can check the transcript online.
Anybody in here has 2 degrees or working on their 2nd degree? No. Okay, so no one's gonna be familiar with this scenario. I was wondering if you can see the historical, and if you see the history of your grades, do you see 2 degrees? And then does your GPA include both majors, or is it just the last major or the current major that you're in? That'd be an interesting question actually. I might have to ask that. I'm kind of curious now. So a table that is in 3rd normal form but not in Bcnf is because we have A and B that are dependent. And then we have A and B that also determine C and D, but C is only determined by B. Well, let's see how this works. So we decompose it. So we take this, and now we have C, 3rd normal form, and Bcnf, because these 2 are giving you this one, and then this one is giving you this one, instead of putting it together. So you're just making another table. So if we had a 1st degree table, and then we had a 2nd degree table, and then we had all of them, all the student IDs from the 1st degree table and 1st degree table, and then the multiple degrees, so which basically made you post-grad and grad, or made you two separate categories, separate you out so you're not all in the same table, then we could be in Bcnf. Because then we have a separate table. Oh, are you working on a 2nd master's? Oh, okay, then you're in this table over here. And then the 2nd master's is linked to the 1st master's table. And then we could link you using the same ID and find you all together. So, which would put us in Bcnf. You put us all in the flat table, then we're not in Bcnf. Because we have some rows in there that are dependent on other attributes that aren't student IDs, that's something else that they're using. Either that or they're just looking under the student ID, and you could pretend like you were never a student before with a new student ID. Who knows? I'm sure there's some interesting things that come out of that. So this one is 3rd normal form, but not Bcnf because it's all in one table. This is a 1st normal form with a partial dependency here. So it's almost like we have a partial dependency that's going on inside. And we do have a partial dependency. If you have 2 primary keys and you're 1 student, we get partial view of you under one ID and another partial view of you under the 2nd ID. It depends on which ID we're looking at as to what we're going to get from a GPA or from a class list or something that's going to come out of that, depending upon how we're doing our query. So here's some sample data for a Bcnf conversion. So we have a student ID, a staff ID, a class code, and an enrollment grade. So we have student ID 125 and 125, staff ID 25 and 28, so this is a teacher. 2 different classes, 2 different grades. So another Bcnf thing here would be to take this here, where don't we have a class code that has only 1 teacher? It would almost like, well, this would be an interesting thing as well to see. Do we have class codes that are listed under staff IDs? Well, we're only going to have 1. So if this was SEN 985, we only have one teacher teaching it, so only one ID would be in here. But we could technically have the same class code with 2 different IDs in here, which could lead to multiple teachers teaching the same class, and then which student is taking it depends on which what teacher they have, is dependent upon which class code they're on. Most schools would have a section ID as well. Here we don't actually have section IDs because we only have one class taught by one teacher because we're too small. So if this particular class was held on other weekends and taught by another teacher, then we'd have to have a section ID to keep track of it. And then we could put this into Bcnf composition. So here we have the third normal form, but not Bcnf, because we have a staff ID and a class code. So we take the class code out and we put it in with a staff ID. This is like a section code that we'd have to do. And then we have a student ID and a class code and an enrollment grade. So this is probably an easier one to kind of visualize in terms of the concept of what is it, how do you know if you're in third normal form, and how do you know if you're in Bcnf? Well, you're in both if you don't have everything, if you don't have a class code that's dependent on a staff ID. So if we take the class code, make it a key, and put it in, now we're in Bcnf. Well, what's wrong with that? Every time we do a search on this table, and this is the grades table, by the way, we got to do a join. So we got to join the class code with this class code in order to get the staff. So if I wanted to print out your transcript grade, in this third normal form but not Bcnf table, it's easier to print this query out. Because now we have student ID, teacher, class, grade, all together. Over down here, if I wanted to print out this teacher, there would be another table we'd have to join to get that teacher. But how often are we going to print the teacher's name out? I don't think it appears on a transcript normally either. So if we did this, depending upon how we're going to use the data in the end, it would make it efficient or not efficient. If we know we're going to use it, like if it were course description, you'd take it out of Bcnf and you'd stick it into just third normal form, no Bcnf. Makes the transcript easier to print, makes it more efficient. Because now we can say student ID, staff ID, class code, course description. Because over here we have class code, we have staff ID, but we're probably not going to print the staff ID, who taught the class. Instead we're going to print, SCN 985, and then what's the description for this thing? And then we're going to print that out. That's a good justification for putting something in third normal form, but not in Bcnf. In Bcnf, we'd pull it out, make it even more difficult. Well, so we could put this into fourth and fifth normal form as well. Same problem's going to exist. What ends up happening is we look at other stuff and we go, well, I think the next level is, let's reduce down the number. We're pulling data out of the database at this point. Because do we need to keep the description of it, along with the teacher of it, along with what year it was taught in? So we pull it out further and we go, well, the section code is going to give us the year and the room and the teacher and all that stuff. So we pull it out, we make it even more difficult. We branch it out into another table, then we have to link another table in just to get the class description. So the higher form we make this, the less efficient it is because we increase the number of joins we have to do. So people have decided that third normal form is acceptable. The third normal form table, we can have something like this here, and it's not in Bcnf. It's just perfectly fine. So we don't necessarily have to be in Bcnf. There's some people that say, oh, we must be in Bcnf. Okay, now we're here, but we're going to take longer to query. So it's oftentimes people will take a Bcnf and turn it into a not Bcnf to make the query run faster because you're trying to optimize things. Or take it out of second normal form and put it, third normal form, and put it back into second normal form. Because if you have a lot of data and you got to do some joins and you got to put things together, do we really care? We're more interested in the efficiency. Let's put some business rules in, because you can have a second normal form table that follows business rules that says you got to call each one of these classes this name. You have to use this name. and then you require that you look it up, and then you have to clean the data. So if it's in second normal form, you end up having to scrub the data more often. But the table itself is easier to query. So you go down just because it makes the table easier to use. The higher you go up, the harder the tables are to actually use. So normalization should be part of the design process. Make sure that the proposed entities meet required normal form before the table structures are created. Many real-world applications have been inappropriately designed or burdened with anomalies if improperly modified during the course of time. Well, that's the other thing too. You come up with this great scheme, and then someone decides, you know, this is great, let's just put the description in here. So we got a class code and then we got a description in here too. It's like, no, because the description goes over here, but we don't want to link it, we just want to print it out. So now we took something that wasn't Bcnf, we took it out of Bcnf, but we left part of the Bcnf characteristic. Or you decided you were going to add a field to a table that never existed before. Now all the existing ones don't have it. So instead you're going to essentially have records that are null in there, or that say FNU in them, because it can't be null. So, or let's say, for example, which actually I think is kind of funny, you know, let's not search on student ID. Let's search on last names. You know how many FNUs are in there? Or that's first name. There's like L and U, last name unknown, because someone used the first name instead of the last name, which is kind of interesting, actually. Not interesting, but it carries some interesting scenarios. So you may be asked to redesign and modify existing databases, and then what you're going to do is start and work this process backwards. So the entity relationship diagramming technique is great if you're building it from scratch. So a lot of people do is they take the existing table and build the entity relationship diagrams to see what the diagram looks like. And then as you're building the diagrams, then you notice the problems. You notice the partial dependencies and the transitive dependencies, because you can't build the diagram correctly, or you can't build it the way you want to build it. And so then you translate it into what you want to do, you find out what needs to be changed, you go in and you change it by creating new tables and pulling data out of one table and putting it into another table and then keying it together. So making the new tables gets rid of the partial and the transitive dependencies for the most part. And then you decide, do we seriously need to be in Bcnf format? And what kind of trade-offs would we have if we put it in? If it's a table that's not being searched very often and accuracy is the more important concept, and an example of that would be running transcripts, then maybe Bcnf would probably be a good idea. You don't normally, when you order a transcript from a school, you don't actually get it immediately either. The reason why is because you're not going to hold all the data into the current table either. You're going to archive it. Depending upon how late you graduated, if this was like 10 years ago, it's already been archived by the year. So when you fill out that transcript request form, say, what year did you graduate? That's the most important thing, because it's going to tell you what archive it's in. What degree did you get? That's the second one they're going to ask you, because maybe you have multiple degrees, and back then they had multiple student IDs. And you're never going to remember your student ID at this point, because you already graduated. They might ask you for your social security number. Problem with that is, like, not every international student, especially 10 years ago, had a social security number. And then not every American had a passport number. And then passport numbers come in different forms depending upon whether you have a US passport or a different passport. So unfortunately, that student ID ends up being the necessary evil that you stick into the system. If I were to go back to a school that I had graduated from and I wanted to get another major, I would hope that they'd be able to find my student ID, but that may not be possible either, depending upon what year you graduated in. And plus, how do you know they haven't recycled the student ID? Gave it to another student? You know, because they actually don't recycle social security numbers in this country for that reason alone. Don't get recycled. Because what happens if you go back and try to look the history of somebody who passed away like years ago? The funny thing is when they look up these, you know, you always see them on TV shows. People buy deceased social security numbers off the internet, or you can buy them at flea markets and stuff. Yeah, those are for sale. Because illegal aliens, you guys are legal, but illegal aliens come into the country and they buy the social security number because the employer needs it. And it's for a deceased person, but when you run the number through, it's still a valid number because they don't recycle them. They don't reuse them. They don't make them terminated in the system. They're still in the system. And then all of a sudden this guy died in the 1950s, and then in 1990 or 1980 or whatever, he starts paying income tax again. It's like, wow. You'd think the government would come out to this person and say, wow, how did you get reborn again? How did you survive the fire that you died in or something, right? But instead the government collects all that money. This is a true story, actually, because I ran into an illegal alien who disclosed this through it was on TV. And then I actually met the person. I met another person who had the same problem, and I went, this can't be true. This can't be right. The government can't be doing this to you. You can pay in as long as you want, but when it comes to collect, you're never getting a dime of that. Because you already died. You can't collect. But what they don't understand is when you get a Social Security number, you're paying into the retirement fund. You're paying funds in to collect funds out. But if it's not your number, well, the problem with the loophole, they're not going to give you somebody else's funds. So the guy who died could possibly collect all this money, but you can't collect it. Which is actually kind of funny. So don't buy a recycled number. It might get you a job. It might be able to have you. So the illegals, they do it because the employers won't hire you unless you have a number. You make up a number off the top of your head, it doesn't work. Because they run it through the system, it comes back, oh, I'm sorry, there's a problem with your Social Security number. So you buy a dead guy's Social Security number. And there's databases, and people just sell them over and over again. So some people might actually be using another dead guy's number that somebody else is also using, depending upon where you got the number. You might have multiple people using the same number, but the number always works from the employer standpoint. You just never will collect anything. Anyway. Which is terrible, actually, when you think about it. Why did they take all your money? Well, you're illegal. You're not supposed to be here. But unfortunately, what happens is then you get medical insurance. You can get everything under this number. But you're never going to have... Yeah, there's a problem with it. Anyway, entity relationship diagram provides the big picture, the macro view of the organizational data requirements and operations. So it's created through an iterative process. So we identify relevant entities, we also identify their attributes and their relationships, and then we use the results to identify additional entities and attributes. And just as we can go through many iterations of the entity relationship diagram to actually create the list of tables, we can do the same thing backwards. So we can take this garbage that we have, this is not garbage, we can go back up to the beginning of this lecture and find the garbage, take that garbage and create an entity relationship diagram out of it, that spreadsheet in the beginning. It's not garbage in terms of what it is. It's good data. It's just not database data. It's not a table database. So anyway, long story short, you'll end up having to do that in the real world because you'll walk into a company and you'll go, what is this thing? And then they won't have any documentation on it. But a lot of the nice database tools these days create the entity relationship diagrams for you. In fact, SQL Pro will do it for you. Access will do it for you. Oracle Tools will do it. So will the SQL developers stuff. They will make, there's a separate option that says entity relationship diagram. It just verifies your tables that you've created, and it tells you whether or not, because once you visually see it, then you know, oh, well, maybe I should break that out and put it into a different table. Because if everything's in one table, there's a problem. If you have multiple tables, how is it keyed together? And then you key it together, you might find that there's multiple keys, multiple problems. And then what ends up happening is when you key it together and you save the diagram, it goes back and it tells you all the problems with the data. Then you got to go clean the data up to go match the key constraints that didn't exist before, but now they exist. So then now you got to fix the data, and that's more troublesome than anything else. So, all right, so that's the end of the database normalization. It is lecture number 6B. I'm going to stop this recording.